Here we have a barium-133 solution. It's barium chloride dissolved in hydrochloric acid with 44,000 counts per second and a contact dose rate of 166 microsieverts an hour. It's quite spicy. And now I can gladly announce that this part of the video is sponsored by Radiocode. The Radiocode 103, a scintillation detector, measures a higher dose rate of 240 microsieverts an hour. That's simply because I can get the device much closer to the sample. It registers around 30,000 counts per second. Barium has two radioisotopes that are quite well known in nuclear chemistry, barium-137M and barium-133. First, some data about the 133. Half-life 10.5 years. It decays via electron capture only to stable cesium-133. This is one of the nuclides where the Q value is not high enough for beta plus decay to occur as a competing process. Produced via neutron capture of stable or primordial barium-132. Specific activity is 943 gigabecquerels per gram. What makes this radionuclide so special? Well, it's produced when natural barium is exposed to a high neutron flux. On this chart of nuclides, barium-132 is still described as stable, but the isotope browser app is more up to date and assigns the isotope a half-life of 10 to the power of 21 years. But what makes the barium-133 so special? When natural barium is exposed to a neutron flux, barium-130 can become the 131 and the 138 can become the 139. This is all true, but barium-133 is one of the annoying ones when it comes to half-life. 11.5 days and 83 minutes that can be easily waited out and then it's gone. But 10.5 years, that's round about 100 years until it's gone. So one must really think about where to store the barium until it decays. Enough beating around the bush. This isotope is important because it is used in concrete of nuclear power plants. So-called baroid concrete is just concrete with an addition of barium sulfide. This addition of barium sulfide increases the density and thus the strength and also the ability to shield radiation from the reactor. Normal concrete has a density of 2.3 grams per cubic centimeter, while baroid concrete has a density of 3.2 grams per cubic centimeter. Therefore, gammas have a lower half-value layer thickness in this. This is the technical term that describes the shielding capabilities of a material against high-energy photons. So, barium is needed in concrete to attenuate gammas, but has an unfavorable side effect. Long-lived barium-133 is also produced. But even in the disposal, this plays a minor role because the radioactive concrete cannot be cleared due to the presence of radioactive calcium-41. The nice thing about barium is that it has many gamma lines, as we can see. On the right there is the gamma spectrum I took with the Radiocode 103. The full spectrum is available on the spectrum library. I will spare you the decay scheme as it's really complicated. In my research for the video, I found that barium-133 was also used to determine the retention times of radium. In one study, barium-133 tracers were injected into 6 volunteers. Why barium instead of radium? Barium is more acceptable than radium, an alpha emitter, and they are chemically almost identical. In general, many radioactive earth alkaline metals were experimented with, for example calcium-47, strontium-85, barium-133 and radium-223. The behavior of barium and radium was indistinguishable, and by 2001 injecting radium was no longer justifiable. But apparently radioactive barium was. So barium-133 was used as a tracer to study the behavior of radium inside the human body. For those interested, 72 to 80 kilobecquerels carrier-free was injected and measurements were done with a scintillation counter. Here's the decade-corrected graph showing the relative whole-body deposition of barium-133 over time after the injection. It accumulates in the bone due to its chemical similarity to calcium, and thus is present in higher concentration in areas with more bones, such as the chest, thorax, and the hip, pelvis. To fill out the video, there are other well-known barium isotopes like the barium-137M. There's a very cool experiment that I will show in the future where you can isolate the extremely short-lived barium-137M from the cesium-137. Cesium-137 decays into barium-137M, which undergoes an isomeric transition by emitting the very well-known 661 kiloelectron-volt line while doing this isomeric transition into the G state. The half-life of metastable barium-137 is 2.5 minutes, and since it's an alkaline earth metal and the parent nucleus is cesium, a a alkaline metal, you can, if you work quickly, separate them both chemically and have a highly concentrated Barium-137M sample for a short moment. There's also another important isotope of barium, the Barium-133. Although it's stable, it is used for dating meteorites, but I hope to make a separate video about that in the distant future. Good, we have learned something new about radioactive barium. There's also an experiment with radioactive concrete and Barium-133, and the video for that is linked down below. A special thanks goes to the Working Group of Analytics and Fundamental Nuclear Chemistry from Dr. Erik Strupp and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. With that being said, thank you for your attention and goodbye.